Well, good afternoon, everybody. This is Gene Bohensky at IR Thermal Systems. And the title of this presentation today is How to Optimize IR Drying Systems Measurement and Controls. And in this presentation, we're going to be demonstrating and educating from our experience deploying IR heating systems over many years. And I think it's a great presentation that Chief Engineer really developed based on his knowledge and experience. And I think that you're all going to like the content. So it's a very good one. So let's get started first with an introduction to our company. IR Thermal Systems was founded in 2020 after the former management team purchased the assets and intellectual property of Radiant Energy Systems and Anderson Thermal Devices. So the management team and employees have experience dating back to 1985. So we are based on a long experience in history. Our core competence is the design and manufacture of custom engineered process heating solutions for improving the performance and lowering the production costs for our customers. We focus on quality and dependability of equipment. We constantly invest in the latest manufacturing technology. We produce our own high-quality component parts. We're focused on continuous heating processes. That's our main focus from a market standpoint. And we're technology independent, and that allows us the freedom to choose the best technology, heating technology, for the customer's application. So what we mainly focus on and how we help our customers are custom process heating solutions, like the one shown there in the picture at the right. They're used for preheating, drying, and curing applications. We do hot air systems, and there's a variety of technologies that we deploy there. We do infrared systems and heaters, and we also do combination and hybrid infrared and hot air systems where the IR is used as a booster. In those cases, adding infrared increase line speeds, reduce energy costs, save space. They also level out uneven temperature or moisture across the web, or we can even heat specific zones across the web to improve product quality and process performance. So we serve a wide range of industries, and they include converting, paper, film, and foil, printing, nonwovens, plastic, adhesive lamination, batteries, which is a big topic today, medical devices, filter media, fiberglass, advanced composites, industrial fabrics, automotive, packaging, wire and cable, textiles, and many other industries where process heating is required. So how we work with your team? Well, we have a team of specialized engineers that will review your existing process or your proposed process. We determine the best technology to use to meet your goals. With our state-of-the-art design tools, we develop a system tailored to meet your target specifications. And we also have a low-cost infrared rental program that allows you to try our technology in your plant. And we'll talk a little bit more about that later. So why choose infrared heating to begin with? Well, infrared heating systems are more efficient with lower energy requirements for the same results. So today, energy costs can be significant. More companies are installing this technology to be more green. The energy is directly transferred from the heater to the target object for a higher heat transfer rate, and they are available in electric or gas-powered versions. So infrared heater characteristics, they include that they are easy to zone for uniform heating of the product and width changes. They have a fast response time to changing process conditions, including quick startup and shutdown in most styles of heaters. They also have a lower initial capital and installation costs, including floor space savings. And they're often added to existing conventional dryers to increase line speed and improve process quality. So let's start with some of the specific topics of our presentation. And the first portion is going to be discussing closed loop versus open loop temperature control. So let's start with open loop. Open loop means there is no feedback to the power controller. So like shown on the right there, You have an adjustable knob on a control panel uh, and on the door that controls heater output as a percentage of power, 0 to 100%, like you can see there. And the temperature controller is run in manual mode, and it controls heater output like a light dimmer. So you're basically adjusting yourself the temperature, and you're really not getting any feedback from the process of what's actually happening there. You're just sending the signal, sending the heat um, out to the field. With a closed loop, what you're doing is you're adding some type of feedback that can control the heater output. And that could be, you can use a couple of methods for that feedback. It could be thermocouples that are embedded beneath the heater element. That's where you're actually measuring just the temperature of the heater element. You can have thermocouples in the air beneath the heaters. That's not something that we recommend, but it is done. You also have infrared thermometers that could measure the actual web temperature. That's where you're actually looking at the temperature of the product itself, and you're feeding that back to the controller to making sure that that's consistent. You also have line speed followers, and closed loop control requires a controller running in some sort of automatic mode where it's adapting the the temperature based upon what the sensors are feeding back. So here's a couple of examples. On the left there, you have the thermocouple under the heater element for heater temperature feedback. And on the right, you could see those infrared thermometers, those black thermometers that are installed for web temperature feedback. That's where you're actually looking at the temperature of the product. So let's look at some advantages and disadvantages of open loop versus closed loop control. So open loop control is naturally less expensive and simpler to maintain, but it requires the operator to make adjustments when the line speed changes. And there has to be some way the operator is going to do that, either by look or feel or understanding the quality. It may not be repeatable and recordable as environment changes. So with closed loop control, naturally you have higher cost because you have to pay for the sensors and the feedback mechanisms. It requires some understanding of closed loop controlling concepts. And the thermocouples still require the operator to make adjustments when line speed changes. With infrared thermometers and line speed followers, adjustments are made automatically as line speed changes. No operator input is required. And infrared thermometers may not work well at very low line speeds or with highly reflective products. But in general, a closed loop system can provide repeatable and recordable process settings and ultimately a more consistent and higher quality product. So let's go over some terms associated with closed loop control. First is PV, or process variable. That refers to the input measurement used. That is the temperature measurement and where that could be located. So that measurement could be the element temperature, the web temperature, the air temperature, or even the line speed. SP, or set point, refers to the constant to be maintained. That is the constant temperature in centigrade or Fahrenheit. So when controlling by thermocouples under the heater elements, this temperature could be high as 1800 degrees Fahrenheit, and is not what the heated web will see. So controlling the web temperatures is usually less than 500 degrees Fahrenheit. And the set point in line speed is a proportional output linearized based on feet per minute, inches per minute, etc. So that you set the temperature in advance based on the line speed, and then it changes according to the line speed. So CV is control variable, and that refers to the output to the heater. So that's usually a control signal to a power controller, like a 4 to 20 milliamp or a 0 to 10 volt DC signal, a typical industrial control signal. That output can be proportional, burst fire, fixed time base, or variable time base. And the proportional control is similar to a light dimmer. For medium and shortwave infrared heaters, proportional control is almost always used because it is the most accurate control for even heating. You have a faster response. There is no visible visual flickering of elements. You have an improved element life, and you have a soft start and voltage limiting that can be used. So let's go to the next topic, which is PID control. PID refers to proportional, integral, and derivative, and we'll go over those concepts in this presentation. So the first, we'll look at proportional. Proportional can be expressed as band or as a gain. For our discussion, we will use proportional band. It refers to a temperature band above and below the set point where the corrective action takes place. And here we're using this diagram that kind of shows the temperature versus the set point and time, and how that works when you're making adjustments. So I'm including the that little graphic on the right. So the output below the proportional band will increase the heater's output to 100%. So the output above the proportional band will decrease the heater's output to 0%, and that is until it comes back to the temperature set point. The higher the proportional band number, the wider the range of temperature control around the set point. And the wider the proportional band, thus the slower to set point and less overshoot. The narrower the proportional band, the faster to set point and greater overshoot. So values affecting stability are opposite of proportional band when using proportional gain. Using only proportional control will get close to the set point, but never actually attain it. So you're actually always getting closer, trying to get your temperature so it performs in a certain way. It's similar to like a thermostat in your house. You know, your air conditioning switches on and off and kind of cycles around the temperature set point. So integral, also sometimes called reset or automatic reset, refers to how often the PID algorithm is recalculated. And that can be either seconds per repeat, that's our default, repeats per minute, and it can allow proportional control to attain the set point. Derivative also is also sometimes referred to as rate control. It can be expressed in seconds, our default, minutes, or minutes. And a derivative looks at the error and adjusts output based on it. Derivative is the most difficult to adjust and is often left at a minimum value for simplicity. So here's a couple of notes. Finding the optimal PID values will give good response control with minimal overshoot on startup. And PID loops can be tuned manually. There are many methods for doing so. For further information, search for Ziegler-Nichols tuning. And many controllers feature auto-tuning, which usually will get close to optimal values. So for the next portion of the presentation, we're going to go over zoning. And the first type of zoning we're going to discuss is IMD, or in-machine direction zoning. So in this type of zoning, the zones follow the direction of web travel, and the heating elements go across the web. Okay, so it's the zones follow in direction and elements go across the web. Less heat may be required in the first zones than in the final zones, or vice versa. Each zone is usually independently controlled with a separate controller and feedback means. And you can kind of see there that you're looking at the temperature across the web is kind of consistent across the web. And so here's another diagram where we have three different temperature zones in a heater that's set up in an IMD, or in-machine direction control zone configuration. You could see that as the web goes by, you have three different heater zones. Now, the second type of zoning is AMD, or across machine direction zoning. With this type of zoning, zones are across the web width and the elements are in the machine direction. This is a little bit more complicated, as more heat may be required on the edge zones to compensate for natural edge cooling due to convection. And each zone can be independently controlled with separate controllers and feedback, or may be biased to the center by voltage limiting SCRs. This is more expensive, but it provides better control, and also a better control of quality when you do this right, because you have issues with sometimes on the web, across the web, you have challenge is making sure that the temperature is consistent. And so in this case, when you have those challenges, you want to use this type of zoning. You can also do combination IMD and AMD zoning. So let's look at some diagrams. Here's some AMD zoning options. There's a couple of pictures here that show one on the top with separate left and right biased edges. You have a 34-inch center zone with a total width being 60 inches. And you can see you have different temperatures for the green and for the red and for the purple there. You also have a different section on the bottom. You can see you have the same 60-inch width, but you also have additional zones. You have the green and the purple as well as the red, and that allows you to give some different temperature bias to separate sections of the web, depending on what makes for the best product quality. Here's another one where you have the left zone, center zone, and right zone of different temperatures. Again, in all these, you have the product flowing from the bottom through the top, so that you could see the web is moving across the zones in that way. So the next portion of the presentation are going to show some tips that really come from our experience on how to optimize infrared heating. So let's talk a little bit about infrared heat dispersion concepts. So we'll start at the left there. Infrared energy disperses in a cone or triangular pattern from the source, similar to visible light from a street lamp or on a dark night. And the further away from the heat source, the less intense or effective the energy transfer to the product is. So we typically recommend that infrared heaters should be about 2 to 3 inches away from the product being heated. And you can see that in that diagram in the center. On the right, we show that elements in heaters should be close to each other in order to overlap the infrared energy. So that first picture there on the right, you can see how it's overlapped. That's kind of the ideal. Some people overlap even further, where the overlap goes to the center of the heater beam on the left. You also have something that's not ideal shown on the bottom, where you have a cool space between heater elements. So you want to avoid that. So let's go to some additional infrared heat transfer concepts. So our experience shows that any water vapor or smoke will absorb some infrared energy and block it from reaching the product to be heated. Using our SFA design with airflow through holes between the element can greatly reduce this. So the holes are important because we can extract that water vapor or smoke and improve the quality. And SF, by the way, for anyone's interested, that's stamped foil. Those are our stamped foil elements that we produce in-house, and something we recommend for long-term quality and longevity on a lot of applications. That's one of the things we make ourselves in order to control that quality. So let's look at some uniformity concepts. Here we have heating elements running in the IMD or in-machine direction across the web. And in such a case, we recommend that the heating elements are skewed so that as the web moves across, you don't get any striping or any inconsistency in the heating. So this we found also improves the product quality. So when we configure a heater this way, we always include skewed elements. The next is building in rapid shutoff devices that allow the heating elements to be shut off quickly in order to prevent damage to the product or equipment when something wrong happens, when either product movement stops under the infrared heat source, or the heater needs to be shut off and the airflow needs to be increased or added to cool it down. So our heater elements are designed for rapid cool down and use contactors to rapidly shut off for safety. In addition, VFDs or automatic dampers can be used to add or increase airflow on shutdown. This is very important because things could happen and you don't want to lose product. So we also include interlocks, heater interlocks. Our control panels are built to NFPA 79 electrical standards for industrial machinery and always provide both branch circuit protection to fulfill code requirements, high-speed fuses to protect the SCRs, and contactors for safe and rapid and complete disconnect of heaters on line stops. So interlocks from customer to rapidly remove heat are done in case of number one, if the line speed falls below the threshold for effective IR heating, if the loss of web tension or web break occurs when you need to stop that heating, or any line stop in general, including an emergency stop. As soon as that's done, you got to shut off those heaters as soon as possible. So let's end the presentation by talking about how to get to know IR heating. So it's ideal to run trials in a lab or your pilot line to confirm oven sizing and desired finished product quality. Sometimes coatings may not be able to take advantage of higher rates of heat transfer and may skin and blister, and may be difficult to work with temperature sensitive substrates. And since infrared is basically a surface phenomenon, sometimes it's harder to dry heavier coatings without overheating the surface. And we include a rental program that allows customers to deploy infrared at a low cost to learn. And here I want to finish up by talking about this. We find this very successful. We help a lot of customers solve their process and quality problems by first rapidly deploying one of our rental heaters. This has shown time and time again how we can save money and improve quality at your processes. Currently, our heaters are available in widths from 12 to 84 inches. They're available in 240 volt, 480 volt, 1 or 3 phase electricity. Rental packages include the heater, a blower, and a control panel. They're designed for a quick trial setup. They're plug and play. And we have rental terms as short as 1 week. And test units are available for running trials in your facility on your line. And that's one way we want to show you how the infrared heating works and will work in your process. So with that, that ends the presentation. You can contact us today with your application. You can email us info@ir-thermal.com or call us at 833-oven-dry.